Chapter 4.3. So we'll keep talking about linear regression. In this section, we'll be adding one more measure that will be helpful to explain the relationship X and Y. And we're going to end with some causation when interpreting the linear regression line and the results. Okay, so let's just look at this three scenarios at the bottom of the slide. So A scenario, B, and C. And as you can see that all of them has kind of downward relationship going on. So if you probably find the fitted line, it's probably all three of them are probably about the same line there. But how can you actually describe the difference between these three scenarios? The part A is all the data set is quite closely on the line, right, on the trend. B, a little bit more spread out. C, there's a little, same trend, but there's a way much more variation. Right? So we kind of need to measure that how much of this trend line or linear regression line explains the data set, data variation. So that's what the R square is. So it's by definition, it's a proportion of total variation that is explained by linear regression. So let me actually make it a little bigger here. Okay, so R square is by definition out of total variation. How much variation you can explain with linear regression line. So variation explained by linear regression divided by total variation. Okay, so that's the definition of R square. So if it is perfectly fitting, so if your model is deterministic model, I guess we used that word before. So everything is on the line. The amount of variation that we can explain using this line is pretty much everything, right? 100%. So if this is the case, your R square will be equal to 1. How about anything? So nothing is actually explained by your linear regression line. So your linear regression line is whatever, that line, but you probably cannot really explain that much about what's going on with the data set. So in this scenario, your R square will be close to 0. It's probably not going to be exactly equal to 0, but it will be actually close to 0. And everything else is in between. So R square has the range of 0 and 1. And if it goes too close to 1, that means your line is explaining almost everything about your data set variation, the variation in your data set. And if it is close to 0, means your linear regression line really doesn't explain too much of it. In other words, R square close to 1 means good fit. R square close to 0 means bad fit. So going back to our different scenario, this one, your R square is probably close to 0.9, 0.8 or so. The second scenarios, I would guess, again, if it's not the actual value, the exact value, maybe it will be 0.7-ish, 0.6-ish. And this one, probably 0.4-ish, 0.5-ish. Right? So you can kind of guess what would be R square back and forth from the scatter plot. Okay, so that's what the R square, coefficient of determination, or R square. So here we're going to talk about the relationship of R square to R. Surprisingly enough, the R square is just actually square of R. So in other words, your correlation coefficient to R is square root of R square. But, R, the range of R was -1 to 1, right? And then R square, and we typically use the capital letter, is between 0 and 1, right? So the way that we explain that the interpret these values are different. Okay, so saying that, let's think about this 1, 2, 3, 4, 5, 6, 7 different scenarios here. If it's a graph, we looked at it in section 4.1 and we're revisiting it now. So here, we're gonna actually start from your R square, since we just talked about R square. But if it's a deterministic model, how much of variation can we explain with a line? Maybe almost everything. How about this line, the last one, perfect negative correlation? Even though it is negative, your line, and line over probably that, right, will explain everything about this data set. So your R squared in this case will be, again, is equal to 1. This guy, no correlation, no relation. Your R squared will be close to 0. This one, again, maybe 0.5-ish, 0.6-ish. This one, maybe 0.9, 0.8-ish. This one, same thing. This one. The difference again, 0.6, 0.8 things are pretty much my guess. Okay, then what's going to happen to R? R again goes -1 and 1. But remember that R actually has a sense of direction. A negative number means X and Y is negatively related. And if it is positive, that means it's positively related. So this guy will be +1. Again, another way of thinking is that you just take a square root of 1, it will be just 1. This guy will be -1, right? Because you take a square, but if it is negative relationship, it should have a negative value there. This guy will be close to 0. This guy, if you take I guess 0.6 to the 0.6 to the square root of it, you're gonna have about 0.7745. So 775, and this one will be negative, right? It's a negative relationship. And if you take the 0.8 square root, will be 0.89. Negative 0.89 will be, okay? And this one, positive 0.89, positive 0.775. Okay, just notice that once you actually take a square root, the value between 0 and 1, this one actually become larger than this value. Same thing happening here too, right? So just notice that. Okay, so that's the thing about R square and R. Okay, so going back to our stack crunch example, we're going to go back to shoe size and height example, and then we're going to actually see how we can find the coefficient of determination, which is R squared. And this question, the last question, is how much % of variation in shoe size can be explained by height, linear regression line with the height. So it's just asking the R squared. If there's another way you ask R squared. Okay, so going back to StatCrunch, there are several different ways that you can do it, but we're just going to stick with this linear regression option. So your X was still height, Y is shoe size, and that's the only thing that you need to do. And if it's the exactly same output that we saw before, and your R square is right there. Here is your R square. So 0.065, 0.065. Okay, so you can say your R square here is 0.0, I forgot, I can write it down here, 0.065-ish, right? Here we are. So what it means is 6.5% of total variation can be explained by linear regression line. So what do you think? It's actually pretty small percentage, right? But that's how you would use the R square. R. Okay, okay. We're going to talk about two different caution when you're interpreting a linear regression line. The first one is about extrapolations. So this is actually the data set from actually a student, the fourth grader. So this particular fourth grader has a really good reading skill. So the students' reading scores are 900, 950, or 850-ish. So that's the range of this person's reading. And these three lines were actually expected 50th percentile, 25th percentile, and 75th percentile. So, in the beginning of the this is the STAR quiz that some of you might become familiar and some of you might not. But anyway, the students are taking this reading test throughout the year. And for this is a median, so they were expecting their reading score ability starts from here, and at the end of the fourth grader for June sometime will be from over there. And this particular person has a pretty high ability of reading it already in the beginning of the fourth grade year. So this thing is only came in sometime September. And with this three tests, what they did is they just make a linear regression line based on these three data points, and then extrapolated. So they kind of guessed it what's going to happen. So according to this linear regression line, by the end of the fourth grader, this particular students will be able to read nothing. That really doesn't make sense, right? So what's going on here? There are a couple things that is going on here. First, the data set is only based on the three data points in the beginning of the semester, beginning of the year. So the reason why this one became going down like that is the third exam was, slightly less than the other ones. So based on real small data set, but more than that, they really extrapolate the model to the way outside of its range of the time, right? So when your things are actually happening around here, it's probably not a good idea to extrapolate too much, and then your prediction power is actually very weak. So be careful about doing that, especially using linear regression line as a prediction. The second one is causation. So typically, when we are looking at X and Y and the relationship between two of them based on your linear regression line, we talk about association. We typically say, X and Y is associated or related. Sometimes some people actually want to use it as a X causes Y, or Y causes X, or whatever. So causation. But to make a long story short, you really don't want to use the causation using the linear regression. So this is some counter example that you really showing that you shouldn't use causation for linear regression. So this is the data set. So the x-axis is here. The purple triangle is the autism. Okay, so as time goes on, we're finding more and more autism there. The pink square is organic food sales. And as time goes on, it actually goes up as well. let's assume that you're taking a linear regression between autism and organic food sales, because it has all upward thing. If you actually draw a scatter plot or linear regression, for example, let me, okay. If you draw organic food sales and autism, what you're going to find is they have this kind of relationship. So the right interpretation will be organic food sales and autism has a positive correlation or positive relationship. But some people tend to say from wrong, incorrect interpretation will be the organic food sales is affecting autism positively. So more and more organic sales, the food sales causing autism, which is totally not true, right? So the point is when you're using linear regression line, don't use the causation, because we're not really talking about causation. We're only talking about association. Okay, so those are two things, the caution that you need to be careful. I mean, there are more things too, but there are two main caution when you interpret the linear regression line. Okay, this is the end of 4.3.